Welcome to the Explainer. Today, we're taking a simple piece of plastic, some motors, and a circuit board, and we are going to build a brain. We're exploring the super fascinating world of drone autonomy, and we're specifically focusing on control theory and algorithms. Now, in our previous discussions, we looked at how drones actually sense the world around them. But today is all about how they interpret that messy sensory data to make flight a reality. We're going to build this digital brain from the ground up, starting with really simple, immediate reflexes, all the way up to highly complex, math-driven autonomy.
Okay, let's dive right into this. Here is our roadmap. First, the basics of feedback. Then, mastering the PID controller, followed by nested stabilization loops, trajectory and waypoints, advanced control and estimation, and lastly, safety and flight modes. Let's get to it.
Section 1. The basics of feedback, focusing on the control loop.
This is absolutely the foundational concept required for any autonomous system. Without it, a drone is basically just an uncontrolled flying blunder. Just look at the clear contrast between these two types of systems, open loop and closed loop. An open loop system is kind of like a basic timer-based washing machine. It just runs for a set amount of time. It doesn't actually know or even care if your clothes are clean at the end. Its action is completely independent of the actual output. But a drone? A drone simply cannot survive like that. It operates in a completely chaotic environment, constantly battling gravity and unpredictable wind gusts. And that is exactly why it relies 100% on a closed-loop system. Just like a thermostat continuously checks the room's temperature to decide whether to turn the heat on or off, a closed-loop drone uses continuous sensor feedback to measure its reality and instantly correct any deviations. It is just this constant, never-ending cycle of sensing, calculating, and adjusting.
Section 2. Mastering the PID controller and managing the error. Let's see how that feedback loop actually builds into the mathematical engine of the drone's brain. The entire goal of this controller is to manage what we call the error, which is really just the mathematical difference between where the drone currently is and where it actually wants to be. The PID controller is made up of 3 distinct parts, and the first is the P, the proportional term. You can think of this as the drone's immediate reflex. If a gust of wind shoves the drone off its target, the proportional term reacts right now. And just like the name suggests, it provides a response that is directly proportional to how far away it is from its goal. So a huge push off target gets a massive, powerful correction, while a tiny little nudge just gets a soft correction. It deals entirely with the present moment. But, that proportional term isn't perfect. Sometimes it leaves a tiny, persistent gap between the drone and its exact target. And that is exactly where the I comes in, the integral term. Unlike the proportional term, the integral looks backward. It continuously sums up all those tiny past errors over time. So if the drone is just slightly drifting to the left for a few seconds, the integral term notices this steady-state drift, it builds up a corrective force and shoves the drone perfectly back to center. It literally remembers the past to fix the present. And that brings us to the final piece of the puzzle, the D, or derivative term. If the proportional is the present and the integral is the past, well, the derivative is the drone looking into the future. It constantly calculates the rate of change of the error. If the drone is rushing back toward its target way too quickly, the derivative senses that speed and acts as a dampener. It pumps the brakes to prevent the drone from overshooting its goal and just aggressively wobbling back and forth. So, summarizing this all up, we can see how these 3 components work together seamlessly to fight the error. The proportional fights the current error, the integral cleans up that past drift, and the derivative anticipates the future to keep everything super smooth. When you hear about someone tuning a drone, all they're really doing is adjusting the strength of these 3 specific reactions to achieve perfect, locked-in stability.
Section 3. Nested stabilization loops, specifically task separation.
So now that we have our mathematical engine built, it brings up a pretty interesting question. How does a drone actually manage multiple competing priorities at once without crashing? I mean, it has to stay level, hold its altitude, and fly to a GPS point all at the exact same time. The secret is nested stabilization loops. The drone essentially separates its tasks by speed. Step 1 is the lightning-fast inner loop. This loop relies on high-frequency gyroscope data to make millisecond-level adjustments to the motors. Its one and only job is attitude control, managing pitch, roll, and yaw so the drone doesn't instantly flip over. Then wrapped entirely around that is Step 2, the slower outer loop. Because that inner loop is so busy keeping the drone from falling out of the sky, the outer loop can actually take its time using slower sensors like GPS and barometers. It methodically handles the higher-level journey, guiding the overall position and altitude. It's really a perfect hierarchy. Survival first, navigation second.
Moving to Section 4, Trajectory and Waypoint Planning, or Path Planning.
Okay, so our drone can hover steadily, and we know it won't flip over. But how does it actually know how to get from point A to point B? Just drawing a straight line between two GPS waypoints is really only the beginning. To achieve smooth, efficient, and above all, safe flight, we have to use sophisticated path planning algorithms. We have grid-based planning, which essentially maps the whole environment into simple squares. We have graph-based planning, which looks at paths and intersections, kind of like a standard roadmap. Then we have optimization-based algorithms, and these are so cool because they compute paths specifically designed to minimize a cost, like trying to reduce the total flight time or save as much battery energy as possible. And of course, absolutely none of this works in the real world without obstacle avoidance, where the drone uses LiDAR or vision cameras to actively detect objects and dynamically maneuver around them in real time.
Section 5, Advanced Control and Estimation, looking at state estimation.
Now, all of this logic sounds flawless on paper, right? But we have to acknowledge a pretty hard truth here. The real world is incredibly messy, and sensor data is rarely ever perfect. I actually want you to stop and think about this for a second. How does a drone actually know where it is when literally all of its sensors, its GPS, its accelerometers, are naturally noisy and slightly inaccurate? This is a massive real-world engineering problem, because if your sensors are lying to you, your control loops are going to fail.
So, the crucial point here is this incredibly elegant solution called the Kalman filter. This is just a brilliant piece of math that performs what we call sensor fusion. See, the Kalman filter doesn't just blindly trust a single sensor. Instead, it continuously predicts where the drone should be, and then it checks that prediction against all the incoming noisy sensor measurements. By constantly balancing its own predictions with fused data from multiple sources, it effectively filters out all that noise. Ultimately, it hands the PID controller an incredibly accurate, smoothed-out picture of reality so the drone can fly flawlessly.
And sometimes even standard PID just isn't quite enough for really extreme scenarios. That is exactly when these advanced algorithms kick in. Take Model Predictive Control, or MPC for short. It actively predicts the drone's future behavior over a short time horizon so it can select the absolute optimal motor commands for really complex maneuvers. Then there's Adaptive Control, which is basically magic for delivery drones. Think about it. If a drone drops off a heavy package, its entire mass and balance change instantly. Adaptive Control adjusts the drone's internal parameters in real time to compensate for that drop. Finally, nonlinear control is used to maintain stability during highly aggressive, high-speed maneuvers where standard, basic linear math just kind of breaks down. Finally, Section 6, Safety and Flight Modes and the Pilot Interface.
Let's walk through how a pilot can progressively hand over the controls to all these complex loops and algorithms we've just spent time building. At the very top, in manual mode, the pilot has complete, total control with minimal computer assistance. This is the raw mode that aggressive FPV drone racers use. Drop down a level to stabilize mode, and that super fast inner loop takes over the job of keeping the drone level, while you just handle the direction. Moving to GPS hold or loiter mode, the outer loops fully kick in, literally locking the drone to an exact coordinate in the sky, which is absolutely perfect for things like industrial inspections. And finally, autonomous mode takes the human entirely out of the equation, executing those complex path planning algorithms we discussed to flawlessly follow a pre-programmed mission. But listen, true autonomy absolutely requires fault-tolerant control. Commercial drones need a real-time safety net to combat calculation latency, communication delays, and just sudden random hardware deaths. The key here is redundancy. By carrying dual GPS modules or multiple internal measurement units, the flight controller can actively compare the incoming data. If one sensor suddenly dies or starts spitting out crazy numbers, the drone immediately detects the failure, completely ignores the bad sensor, and switches to a backup, or it triggers an emergency safe descent. It is a vital layer of self-preservation. Which brings us to a really provocative thought for the future. We have spent this entire explainer building a brain completely out of rigid human math and carefully programmed control loops. But as AI reinforcement learning starts allowing drones to literally learn how to fly through pure trial and error and simulations, and as swarm algorithms let hundreds of drones autonomously coordinate together for things like search and rescue, what happens when drones no longer need our PID math at all? What happens when they learn to fly entirely on their own? It is a fascinating evolution, and I really hope this foundational look at control theory gives you a much deeper appreciation for the amazing technology hovering right above our heads. Keep learning, and I'll catch you in the next one.